Okay, IBSL1. We are back with 11.4. Today we're going to talk about the law of cosines. So we've already learned about the law of sines, where you take the sine of an angle over the opposite side, and you can set it equal to any other sine of an angle over the opposite side. But there's certain triangles where the law of sines doesn't really work. I kind of save the law of cosines as a last resort because it's way heavier on the computation than a law of sines. Like if you can use law of sines, do it all day long. But law of cosines, it still works with any triangle, but I think it's doing too much sometimes. But there's some where you have to use it. So first up, there is a proof of the law of cosines on page 489. And if you are interested in how it was derived, please check that out. But I essentially am just going to deliver the law of cosines to you guys. So the first part of law of cosines, well, first notice that all these little letters are directly across from the big letters. So it's the same relationship we've had with all these triangles, where like the small sides are across from the big letters, which are the angles. So the law of cosines, I always remember that it starts a lot like the Pythagorean theorem. So let's start with this one. C squared is equal to a squared plus b squared. But then there's more. You then have to subtract 2 times a times b times the cosine of capital C. So some things to notice about this equation. Notice that it starts with small c and ends with capital C. So it always has this bookends of the same letters. Now, the other thing to notice is that these two letters have a repeat performance here and here. So c squared equals a squared plus b squared, then minus 2 times these two things, then times the cosine of the capital letter, which is here. Now, as if this weren't complicated enough, you could also say there's another equation where you could say b squared is equal to a squared plus c squared. But then, once again, you have to subtract 2 times the two guest stars, which are a and c, and then times the cosine of capital B. Because once again, if it started with lowercase b, it needs to end with capital B. Now, there's not just two versions of the law of cosines, there's a third as well. A squared is equal to b squared plus c squared. Can you guys see the pattern, what it's going to be? Then it's going to be minus 2 times the guest stars, then times the cosine of the bookend, which is capital A. The book also delivers like 3 different versions of these equations to you guys where the cosine is solved for, but I think you should just do algebra for that situation. So I'm going to do an example like that rather than have like 6 formulas for this. I think it's one. You just need one formula. It's this. It's something squared equals something squared plus something squared minus 2 times these somethings that were here, and then times cosine of the capital something that was here. The rest of them are all just the same ingredients, just mixed around. So that's the basic structure of the law of cosines. Let's take it for a test drive. First up, this problem requires the law of cosines because, look, if I try to find an angle and opposite side to use the law of sines, like I know this angle, but I don't know this side over here. So I can't use that relationship. The same way over here, I know this, but I don't know what this angle is. And the same could be said for this side and this angle that we don't know the angle. Now, if there had been another angle given, like, you know, if this was 19 or something like that, then you could use, like, subtract these from 180 to find this, and you could use the law of cosines and blah, blah, blah. But we don't have any of that. One thing I always notice about law of cosine situations is that sometimes they're set up in this sort of sandwich. And here's what I mean by that. Here's like slice of bread, and then there's an angle between it, and then slice of bread on the outside. So it's like a side angle side is when the law of cosines comes in handy. So let's see. We're going to find BC, which BC is directly across from capital A. So let's call that little a. So I'll start with the equation. A squared is equal to b squared plus c squared minus 2bc times the cosine of capital A. So let's plug in all the ingredients we know. We don't know little a. We do know little b and little c though. That's 17.9 squared plus 14.7 squared. Oops, sorry. Minus 2 times 17.9 times 14.7 times the cosine of 62, because 62 was the a value. Now, this whole side is just calculator work. So if you're very careful, by punching it all in, you could all do that all in one line on your calculator. So you could do 17 plus 9 squared plus 14.7 squared minus 2 times 17.9 times 14.7 times the cosine of 62. And then make sure all your parentheses are good. Boom, that's 289.44. So A squared is 289.44. And I'm rounding appropriately. I'll just keep that number in my calculator, but for the sake of the video, I'm putting the rounded number up there. Then you just need to square root both sides. So I square root, keep the same answer. So A is about 17.01. Now I realize that I took the square root, which means that I should probably do the positive and negative, but since we're dealing with a triangle that can only have positive sides, this is the side. So BC is about 17.01 centimeters, because we did have units on this one. So in terms of the law of cosines, this is probably the easier type of law of cosines because this entire right side was all numbers and it was just, calculator work. The next example is slightly more advanced because we have to solve for something on that side. Notice with this triangle, first of all, we're going to try to find angle A. So we're going to find this right here. Notice that this is a side, side, side situation. This is another time where you have to use the law of cosines because you can't use the law of sines. There's no angle opposite side matchup because we don't know any angles, so we can't use any of it. Now we're going to find angle A, which means we're going to use the same equation again. Really, book, you could have switched it up to one of the different letters. So we're going to use A squared equals B squared plus C squared minus 2BC cosine capital A. So let's plug in everything we know. Little a is directly across from capital A, so that's 18 squared is equal to, now little b is directly across from capital B, so this will be 21 squared, and then little c is directly across from capital C, so plus 27 squared minus 2 times 21 times 27, the guest stars, and then we don't know what capital A is. Okay, let's start to simplify things. 18 squared is 324. 21 squared, I don't know these off top, so I'm definitely using a calculator. 441, and then 27 squared. I know it'll be an odd number. 729. And then minus, well, we'll just do just the 2 times 21 times 27 part. So 2 times 21 times 27 is 1134. Whoops. Okay. I guess the next little simplification we could do is the 441 plus the 729. 1170, so we get 324 is equal to 1170 minus 1134 cosine of A. Now, I'm purposely going to pause here because there's a mistake that some people make here. They see this 1170 minus 1134, and they'll subtract those two things and then leave the cosine of A there. You cannot do this because you're breaking PEMDAS. This right here is one algebra chunk because it's glued together through multiplication. So you cannot do the subtraction before you do the multiplication. So what we have to do is actually subtract 1170 from both sides. That's the correct next move. So 324 minus 1170 is negative 846. Equals negative 1134 cosine A. Excuse me. And then we're going to divide both sides by negative 1134. So divide that by negative 1134. And we get, you know, like, I'm going to put a rounded decimal up here. 0.746 is about cosine of A. This is when you have to do an inverse cosine. So you could do inverse cosine to get the cosine away from the A and get just the A on its own. Now on my calculator, I'm not going to do 0.746. I'm going to keep that long decimal because the longer the decimal, the more accurate the answer. So second cosine of the answer is 41.75 degrees. Now, you might be thinking to yourself, well, Mr. Jolly, we just did an inverse cosine, so that's the one in quadrant 1, but wouldn't there be another answer in quadrant 3, or quadrant 4, excuse me? Yes, that's true, we would, but anything that's in quadrant 4 is going to be an angle that's like bigger than 270. And remember, we're solving for an angle in a triangle. So any angle in a triangle certainly has to be less than 180. So we don't care about the other cosine answer, it's just this one right here, 41.75 degrees. If I were to beef up this problem for a test, I would probably give you this triangle and say solve for every angle. Now, the students that know how to do the law of cosines really well might spend a ton of time doing all this same process here for all the other two angles. But remember, now that you have an angle, like you know that this is like, you know, about 42 degrees or whatever, that you could use law of sines now, because now you have a solid angle and pair relationship. So then you could set up a law of sines, excuse me, I'm getting confused, for this side. So you could do law of sines for that. And then for the third angle, once you have B, you could just subtract it from 180 to find this one. But yeah, just a heads up of a possible test question is like I give you all three sides of a triangle and ask you to solve for all three angles. All right, you guys, that's all I got for today.